So, a quick bit about me. My name is Charlie Gracie. I'm a senior software developer at IBM Canada. I've been working on the J9 Java virtual machine at IBM for over 10 years now. I've actually had lots of different roles on the team, but majority of the time it's actually been focused on garbage collection technology. Currently, I'm the project lead on the Eclipse OMR project, which I'll talk a bit more about in a minute, and also a committer on the Eclipse OpenJ9 project. So today, I'm going to quickly cover the OpenJ9 project. I don't know if anybody here was at Toby's talk yesterday, but he did a sort of a deep dive on the J9 VM itself. But I'll just introduce the project again quickly for people who weren't there. And then I'll sort of go into the overview and details of just garbage collection, just for, I assume everyone's aware of garbage collection, but I'll throw up 1 or 2 slides to just discuss it quickly. Then I'll go into our GC technologies that we have in the OpenJ9 VM, and talk sort of about all the sort of different phases they have, the benefits and drawbacks of each collector, and then I'll hopefully have some time to open it up for questions. So the OpenJ9 project was created last September in 2017. It was actually a lot of work for us to get it out there, but it was taking our closed source Java VM that we've had for almost 20 years and making it available to the public to be able to work on or to use and not have to go through an IBM product to get it. So the project is at the Eclipse Foundation. It's out there under dual license for Apache 2.0 and the new Eclipse public license version 2.0. We're always looking for more contributors or people to go try things, so please check out the project if you're interested. To actually be able to get an OpenJ9 binary, you need to actually build with OpenJDK. The OpenJ9 VM is not actually a replacement for OpenJDK. It is an alternative for Hotspot. So you go get and actually check out OpenJDK. There's a few patches, but we have a repo that has those in it that then will actually go and build our JVM instead of Hotspot. So really, it's pretty much the exact same class libraries, just with our VM and JIT. And there's this project called Adopt OpenJDK. I believe it's based out of London with the London Jug. And they are actually building OpenJDK binaries for all the different, well, at least 2 different JVMs right now. They're building with Hotspot and with OpenJ9. And hopefully in the future, they'll also be building other vendors' VMs there as well. So it's kind of a nice central place to go get OpenJDK pre-built binaries other than just from your Linux distro. So a quick promo for the Eclipse OMR project. It's really the basis for the OpenJ9 VM. It was created a year before as an open source project to basically make our GC, JIT, and other runtime technologies available for other runtimes, not even just Java. So we realized that a bunch of our GC tech and JIT tech could easily be used by other runtimes to actually provide improvements there. So we've made this language agnostic version of our code available. It's out there. It's still actually being consumed by OpenJ9 every day. It's not a project we just put there. It is actually still being used to run our VM all the time. Sorry. So garbage collection, the reason I'm here to talk to everybody. I assume everybody is a Java developer and knows what a GC is, but garbage collection is really basically just automatic memory management for the developer in Java. It kind of removes the burden from for the Java developer to actually have to worry about freeing all of their memory at the appropriate times and that sort of thing. So there's some big positives. You get the automatic memory management, but I think what a lot of people sort of forget at times is it also helps reduce a bunch of different kinds of bugs that can happen. So one of the big ones is regularly we have new guys working on our team and things. We're all in C++ and C. They'll always be missing some null checks or end up freeing things twice, so we get dangling pointers pretty regularly. Java doesn't quite remove those from you, but it actually makes them a bit harder for them to happen. Maybe even harder to debug it once they do. But with those benefits, there are actually some negatives that a lot of people actually don't talk about. So one of the big negatives is that depending on your garbage collection technology, it's actually using a lot more native resources than you've actually expected it to or told it to. So if you were to start up a JVM and say, I want to run with a heap of 200 megabytes, depending on which VM and GC you're using, your process size might be 1.5 gigs, 2 gigs, 3 gigs, and a lot of that could actually just be data structures that the GC is using itself to perform the garbage collection. The other big negative is, everyone knows, unpredictable pauses in your application, varying lengths. There's all kinds of other runtime costs that may also be attributed to your runtime based on the different GCs. There could be write barriers and read barriers depending on the policy. Actually, one of the biggest also slowdowns is actually coalescing all of your threads to be able to get to the point so you can do a GC. And then the one that everyone forgets is when you let your threads go again to start executing, depending on what kind of mechanism you're using to coalesce them, that can actually take quite a while for them to actually all get back up and running again. And also the application will have very little control over when memory is reclaimed. Of course, you could call system GC all the time, but it would make all the GC developers very unhappy. So quickly, my team's goals over the years, and I've been there for a while, and these are sort of passed down from on high from the older guys when I started, is really for our GC development, we really focus on implementing reusable technology. So as I go through some of the different policies as I'm going forward, you might notice that I'm say, oh yeah, I showed that before, it's the exact same thing, so I'm not going to step through it again. That might come up a few times because we actually are using a lot of the same tech over for different types of collectors. We started originally as an embedded JVM. So actually, one of our main goals has always been use less memory. That's including in our native memory that we allocate off to the side, actually, and on the heap. So our GC will actually be very, it's the opposite of aggressive. If you don't specify XMS and XMX to be the same, you leave some space, we will tend to actually not expand your heap as aggressively as all the other collectors. We believe that we have enough throughput in the GC that it's actually still comparable, but actually a lot of applications in runs times would actually prefer to use less memory, so that's kind of where we focused. And sort of against that is also provide highly scalable technology. With the big point of still trying to increase our scalability without actually impacting our single-threaded throughput. It's always a huge challenge, but most of the time if you spend some time, you can actually work around anything you've caused and get back your single-threaded performance. Oh. So the GC policies I'll talk about today, I'm going to go through our op throughput collector, which is just a basic stop-the-world collector that runs all of its different phases in parallel. It's probably got the longest pauses out of all of our collectors on any given run. But it does have some benefits if you're running in a really small heap. If you're running somewhere that doesn't actually require a lot of GC activity and you're not really susceptible to problems with long pauses, this can actually give you some more throughput than some of the other collectors. It doesn't have any runtime overheads that some of the other collectors have in those types of things, so it can actually be a benefit. Opt-average pause is our concurrent collector, so it's basically the same collector as above, but it will go and run the mark and sweep phases in concurrently with the application. GenCon is our generational copying collector, which was similar to what Hotspot had as their default collector till recently. And then we have balanced, which is our region-based collector, which is pretty much the same type of idea as G1. We've decided not to make it our default collector yet, or maybe ever, but it's a very similar type of tech. And then last, these were kind of in order of what we implement them, except for Metronome. it was implemented way before balanced, but I'm leaving it to last because it's now sort of the new thing that people are wanting to talk about again. So it's our incremental soft real-time collector. And I'll get more details on it in a bit. So op throughput is a parallel global collector with all of its phases are in one big stop the world. There's nothing happening outside. You stop once, do all of the work, and keep going. Everything is happening in parallel. And we have usually only running our mark and sweep. We try to avoid compacting at all costs because it's actually a really slow operation. But if you actually need to, so you don't throw out of memory, we'll compact. And just as a note, so a lot of these, all the GC policies, I'm going to kind of call out the extra data structures that are any size that we allocate. So we allocate a mark map and work packets. They'll probably grow your footprint by the mark map by 1.5% to 2%, and your work packets by a fixed 3% of your XMX. So the op throughput heap is just a flat heap. It's one big contiguous block. But it actually is divided into two logical memory areas. We have a regular small object area and a large object area. The large object area is really a last resort. It should be the last resort object area and not large, because we actually won't directly put large objects in there. We actually will still favor and try to put everything in the other area first, as long as they fit. And then so you wouldn't throw it out of memory, we have this sort of last ditch area. By default, it's about 5% to 1% of your heap size, but it's configurable, and most of the time it contracts away if you're not using it. So our allocation is, for this one, just a simple first fit. OpenJ9 has TLH allocations similar to Hotspot's TLab allocations, so it should be very similar to everybody. So I'm just going to step through. So if you're allocating here, you would actually allocate all the way over till the heap is full, or at least till SOA is full, and then you're going to go off and you're going to perform a GC. So I'll quickly run through here. This is sort of like a time scale. So if your application threads or the blue threads are running, you would actually have a GC start and an end. This will be pretty simple because these ones are a simple collector. And again, off application threads, GC, application. So how does our GC actually work here? It's divided into 3 phases. The first of which is our marking phase. That's where you're going to go actually find all of your live objects. Sweep is actually where you will go and reclaim your memory for these dead objects. And compaction, which would defragment the heap if you actually need to do it. We measure a lot of heuristics for this to try and avoid it, but if it does come down to it, we will go and do it. So to step into marking, let's sort of zoom in on a heap here that has, I don't know, 16 objects, or at least a part of it. So how will we go about actually finding the live objects and keeping them alive and finding the garbage? So the first thing you need to do is actually have a root set. So this is sort of the primordial list of objects that the JVM knows about that will actually keep the rest of your heaps alive. So these are things like classes, class loaders, intern strings, thread stacks. Majority of your objects are probably going to be found alive from your thread stack. It's probably the biggest reason to keep things going. All right. So in order to keep track of which ones are alive, we actually have a mark map. The mark map is basically has 1 bit to represent every 8 bytes of your heap. So it's approximately 1/64th of your heap. And what we do here is every time you mark an object as alive, you'll atomically set a bit into this mark map, and then you can always look later to see if it was marked, so we don't end up marking things twice. So just to step through quickly, if we were going through the root set, we found object A. What we would do is we would go mark A in the mark map. But one of the other things we do is we actually have this work stack. So this is how we basically drive all of our parallelism and work sharing throughout the GC for a lot of our collectors. We always have sort of an input and an output stack. These can be varying lengths. They're usually fixed size, but depending on early on in a GC or near the end when you don't have as much work, we will shrink them down so that you can hand out work quicker to other threads to keep parallel the whole time. So in fact, when we mark this object, you push it on the work stack. And then you'll see, we'll step through quickly, all the ones that were referenced from the root set are now all pushed on the work stack. If that's it for our root set, how would you actually go and figure out the rest of your objects that are alive? So we get rid of the the root set, and let's talk about our work list. So every thread has these packets, but when it does finish off work or things, it puts it onto a work list so that other threads or even itself can go get it again. So at this point, at the end of roots, whatever was left, all threads would flush all of their packets over onto this list. This is just a small list if you only have a few number of threads, but to make sure that we can keep scalability, there's all kinds of tricks we play with creating multiple lists here and maybe not always giving up your packet to keep parallelism up. So once we have the work list, we would take one of them now as the input packet. Oh, well, and we should actually make some references here so that we can actually have something to collect and follow. So with the input packet, what you would do is you will pop one of the objects off. So we pop L object off the top of the stack, and we walk its references. So at this point, it only has one reference over to M. So we would check the mark map. If M isn't marked, we mark it and push it on an output packet. We'll do the same through I. I'm pushing K, D, F. And then when we pop A off the stack, it actually, its first reference points to D. D is already marked in the mark map, so at that point we just move on. One of the key points of how our GC works is that you'll never process an object twice in any of the standard cases. So there's nothing to do there. Get B and push B onto the output packet. So output packet was full, it would get pushed over onto the list again. And at this point, all the threads would sort of go through recursively pushing and popping things off of that list and working till there is nothing on the list anymore. At that point, the GC is actually finished the marking phase. There are some other clearable parts of a GC, but I won't get into those today. If anyone wants to know more about them, I can talk about it offline. But they're just to like clean up the VM list for reference objects or finalizable and get them ready to be processed. So once we're done marking, now we actually have to give back memory. So we still don't have any back, but we have this mark map that has that can tell us all the data about which objects are alive. So for sweeping, what we do is we actually look for zeros or nothing in the mark map. So, and for every zero we find, we'll create a free list entry. If there's multiple in a row, it would be a bigger free list entry. And just keep going until they're done. But that would be, we would create a free list entry for every object. That's the principle of what we're doing. But in fact, we actually would only create a free list entry for a block of objects being dead that's at least 512 bytes. So you have to have at least 64 zeros in a row before we would actually create a free list entry. So if we look at this example, and I'll pretend that the single blue squares are 256 bytes, and the double one's 512, just because it works out easy for me, what we would have actually only got is a free list that looked like this. So our free list now actually is only about half of our free memory on the heap. That's not a great answer, but having really large free list entries actually does provide much more performance improvements for your allocator and things, and saves you a lot of time in GC. So as long as you can keep up with this, this is probably the best answer for your application. But what happens if it isn't and you're not actually getting back any memory? Well, then we'd actually have to go compact. The compactor in OpenJ9 actually needs memory to actually keep track of where objects are going. But because we don't like to use any extra memory, we actually just steal our mark map or some large portion of it. We compress it down to a smaller part, and we use our mark map actually for our compact table. So what the compact table is basically a list of offsets for memory areas that how far they slide down in memory. So our compactor basically is just a simple sliding compactor. Objects will move from the higher addresses down into lower addresses to make bigger blocks of memory. So that would work sort of like this. So we'd see 1 move down, F would move down, and every time we move something, that memory area is getting associated in the compact table with an offset of how far it shifted. Luckily, these are all easy numbers because I made them work out that way. So at the end, we would then have all of this compact data, and our objects are all moved. The next step would be to say that's our new free list entry, but I left out one big step so far. I've moved all of the objects, but I haven't updated any of the pointers to where that they were pointing at each other. So basically, this is the reason that compact is actually not a great thing and is really slow. At least in RVM, I know there's some slightly better algorithms, but this is how we've got it implemented. And so at this point, you actually have to walk every single live object in your heap again and find every single reference to another object and update it to the new pointer. So that basically has just destroyed your entire cache, if copying it already didn't, and you're spending a huge amount of time going to update this list. Luckily, the update is actually trivial, but it does mean you have to walk everything. So if we looked at this object A, one of the previous ones, it actually pointed at object D. So what we would do, we know D slid, so it was in the first memory area, so we could tell by its address that that's where it was. We get the offset. So what we store into the field 1 now for this object would actually just be the address that was there minus the value of 256 that was in our offset, and then we could store it and keep going. So that's sort of the quick overview of our op throughput collector. The reason I covered it is I don't think many people would actually use this collector, or possibly the next one I'm going to talk about, but it's sort of the basis for all the rest of our technology. As I go forward, a lot of these pieces are still used, so having the explanation in the simple collector, I hope, is actually easier for people to understand. So I'll move on to opt-average pause. This is a concurrent global collector where we actually will go and do almost entirely all of this mark and sweep work concurrently with your application. What happens is we have 2 stop the worlds at the beginning, one at the beginning, one at the end to kick off the GC and end, but that's basically the only stop the world parts, and they're very short. We utilize a low priority background thread to go do a lot of the work. The fact it's low priority means it won't interfere with your application. That's a plus or a negative depending on who you are. If you're going to not complete your GC, maybe you wanted it to go faster and take over CPUs, but it's a choice we've made in the past to help with a lot of the workloads we were on. The one big difference, I think, for our concurrent marking story that I'm not aware that any of the other JVMs actually do is our application threads actually will pay tax and do the concurrent work as well. So it'll be a bit more obvious in a few minutes. But yeah, the application threads themselves will have little micro pauses, not all at the same time, at individual times where they will do pieces of the work. So this improves your stop the world pause times quite a bit and your application responsiveness. But there are some drawbacks in the fact you will have more frequent GCs and you will have introduce now the first time that I'll talk about an object write barrier. Because now it has more things to do, it also has a new data structure called our card table. So the heap, very quickly, is the exact same as our op throughput, of course. Allocation is the same to start out. But what happens is once you've allocated across enough, we want to be able to kick off the GC before you run out of memory. So we have a bunch of heuristics. In the first GC, they're very basic ones. It's some static sort of threshold of how much of your heap is left before we'll go try, based on some allocation rates that we've been tracking. And we'll go kick off a concurrent collection at that point. But what happens then is you'll see that your application is actually still allocating. And allocates up to a point where we're going to finish the GC. And you'll see at this point that I actually finally drew something actually allocating in LOA. That actually happens quite regularly in opt-average pause because we'll actually try to put something there to let the concurrent finish itself off. So this is a place where we would actually allow things to go in there if they're of the appropriate size pretty quickly to allow us to finish our concurrent work. So again, a quick sort of flow diagram of how it works. So your application is running along in parallel with itself. You'll actually have a very short pause compared to the other ones I drew up before, where we're actually going to go in and kick off the GC. I guess it's kind of a bit different too than a lot of the other collectors that are doing concurrent. Basically, the only route we scan at the first kickoff is actually thread stacks. So we'll scan all of the threads that were at a safe point. We don't have to be at a safe point to do this kickoff. Not all threads have to make it there, but any thread that is, we will scan it. And then we'll set them up so they'll scan their own later. But that's basically it. And then we go off and let the application run again. So most of our route scanning even happens concurrently. So the yellow arrow at the top, that would be our background helper thread that's going through and doing work. But you'll notice the application threads at different times actually will stop, or application threads will stop and do pieces of GC work for us. That's great because it lets us keep up. We sort of have a tax and spend sort of model. If you're allocating and you come out and you need to pay some tax, well, if we've already paid enough, if the concurrent thread has already done enough work, you can kind of just skip and go. But if it hasn't, you can actually, at some cases, which is the downside of this, kind of get a storm of your application threads all trying to pay tax at once. We limited them to the number of CPUs. Of course, we don't want to have people blocking on locks or anything waiting to do work. Just let them keep going. They don't have to pay tax. But if you do get to the point where you have all threads paying some tax, that's kind of just like a stop the roll collect anyway. It doesn't happen in practice that often. We don't see it as a big thing, but it is a potential problem that could arise if you were using this type of collection. So then once the GCs decided we've done enough of our marking work and tracing work, we would have another stop the world pause where we would go finish off the marking, and we would actually start the sweep. We would sweep enough bytes to satisfy some calculation of what we need quickly, and then we actually let the same tax paying that we were talking, the same code, come in for the application threads, and they will actually go do the simple sweeping to allocate to finish sweeping the larger chunks of free memory. That doesn't actually happen in that often, but there will be times when the application threads would do that. And so again, just a simple show a second time through, different threads paying different amounts of tax. And then we're on. So I mentioned that opt-average pause now has a write barrier. I'm not sure if everybody's super familiar with what that is. It's basically something that on every time there's a write of object foo.the field equals something, every time you're storing, we'd actually have to get in and do some work with the GC. So why is it required in this case? So if you had this simple object A pointing to object B, at the point where we were doing our concurrent marking, if we've already successfully marked and scanned object A, we've then possibly gone off of marked B. But if something comes along at this point and changes the pointer to only point at C, if that's now the only pointer to C that we have, at the end of the GC, we'll collect C, because there's no way we would find it anymore. Even though it's clearly alive because A is alive, we won't have it, so we'll collect it. So what the write barrier does is allows us to get in at this point when the GC is active and track these types of things so that we can actually go back and make sure the C is kept alive. So how is this one implemented? If you had this simple function where you're just going to set a field, I doubt you would write your function like this, but to show the example, you're setting field C, object C into field 1 of A. What the interpreter would actually do for you, you would think you're only executing that first line of code. What the interpreter has actually done is after you've done the store, it's gone to check to see if we're actually in the middle of a concurrent GC, and if we are, it will actually go and dirty our card in the card table for object A. And you might ask why A and not C, but it's because we already know that there's a chance that A is marked, and we'll have to scan it later. We don't want to do any marking or anything in the barrier because that's too costly. This is just a simple thing that we can come back later and handle. So to quickly explain how that's handled, this will be sort of the simple example again of our A pointing to B and then switching. So if we're in the middle of a concurrent and we switch this over to B from B to C, what we would do is we would actually go into our card table, and for the card representing the area of A, we would go and just set it to 1, saying that that's now dirtied and we have to process it later. The card table is kind of similar to the mark map. It's not on a per bit basis, it's actually on a byte basis instead, and 1 byte of the card table actually represents 512 bytes of the heap. So we don't have to do this as an atomic operation because multiple threads could all write to this byte individually, but they're all going to be setting it to 1. So it doesn't matter whose write of 1 wins, we're okay. So now that we've got that point, if we're back in the GC, so the basics of the rest of the GC is basically 100% of what we saw in op throughput. It uses all the same packets. It does the code's actually literally the same. It goes through the same code path. But there's one extra piece of data that has to be done at the end. So near the end of marking, we have to go through and process all of these card tables entries to see if we need to find any more work. So what we do is we'd end up walking the card table. We'll look for any card table entry that's a 1, and then we go to the mark map area that's associated with, and we'll look for objects that were marked. Because anything that was marked might have had something changed under the covers on us. So everything that was actually marked, we'll go scan again and process it as if it was being scanned for the first time. So we would go over, it has a pointer to C, C is not marked. We'd mark it. That again would trigger everything to be pushed onto our work packets, and after our card table scanning is done, we have another one of the phase again where we just run through the work list until it's complete. All right, so the next policy is GenCon. GenCon, the name is our generational copying collector, but the name itself is actually Gen for generational and Con for concurrent. So most of our collections are happening in our generational collector, but we do also have our concurrent global collector for the times where we actually have to go do a global collect. The whole idea of the generational collector is to basically, there was like the weak generational hypothesis that basically claims that objects in most applications tend to either have very short lifetimes or very long lifetimes. So if you can target collecting the objects very young in their lifetime, you can probably get a very good return on investment for your time. So this GC targets that and tries to take advantage of it. Again, it has to introduce another write barrier and complicate the write barrier, and it grows another data segment for copy scan caches, which I'll talk about in a minute. So the heap layout is different. It's divided into 2 areas: nursery, which is where all new objects will be allocated, and tenure, which is where they'll get promoted to, or in the case of things like classes or intern strings, they just get directly allocated in there because we expect them to have a long lifetime. But our nursery is now subdivided again into 2 logical regions. It's divided into your allocate and survivor space. Pretty easily from the names, allocate space is actually where all of your allocation will have, and survivor space is used for a destination for our garbage collection. So it's all the objects that survive a GC will end up there. To start out, the split between allocate and survivor is 50-50. But as the GC goes on and starts to keep track of how much garbage, live objects are after each GC, it will slowly tilt the allocate space to be much larger. And it can go all the way up to 90%, which happens actually for most runs. So if we wanted to look at allocation quickly for the GenCon, you actually have a lot less space because you're only going to allocate in the side of allocate space. And I showed here that there were, if you were early in a run, you're probably also going to allocate some tenure space objects. So once you've finished that, you're actually now going to go off and have to do a scavenge. So again, starting off with a little flowchart of what it looks like. And this is probably the GC why I did this, because it's actually interesting. We will actually have a scavenge as we're going along when that fills up. Again, the application runs another scavenge. But because we actually have our concurrent collector going as well, as if you need to, you can actually have a concurrent global start as you're going along. Come back and have the application to continue running, doing the concurrent work in your concurrent background thread. But in the middle of it, you can safely pause all the VM and actually do a scavenge as well. It doesn't cause you to abort the concurrent. It doesn't actually really have any impact on it all, other than it slows down all of the threads to do the GC. So once the scavenge was done, you'd come back and continue your concurrent, hit the global end, and you're done, and all the threads go off and continue executing. So with GenCon, I mentioned that we had a write barrier. So why do we have this generational write barrier? The other barrier was not as obvious, but this one is pretty obvious. If we're only going to be collecting the nursery, you actually need to know what objects in tenure space point at the nursery. You have a bunch of choices how to handle this. You could walk the entire old space every time. That probably would not speed up your GC in any way. Or you can have some sort of way of tracking which ones that they are. So we do the latter of tracking individual objects. So again, how it's implemented, our simple example. And now instead of having the other concurrent code, your barrier actually looks like if your first object is in tenure space, and your other object is not in tenure space, then you'll remember the old object as something that we have to come back and process later. This remember is atomically adding this object to a list so that it can only ever be there once. There's no need to have duplicates. But this one also has our concurrent barrier as well now. So if you're actually running in this mode, this is actually what the interpreter does for every store that you do. You'll have to go through both types of barriers, which in the best case scenario is actually only 2 extra conditional checks. But it can start to be quite a cost. Luckily, we have just-in-time compilers, and those guys are really good, so they can actually elide a lot of these barriers in different places, depending on what the code's doing. All right, so now that we talked about the barrier, how does the generational collect actually work? So again, it's going to start out, you're going to have a root set. As course, that's basically how we drive all of our GCs. From this root set, I'm going to start going through, so we'll go with A. But the first thing we need to do is we actually have to have something we're going to do with this object. So again, we have sort of a per thread work list. And in this work list, we have a scan cache and a copy cache. They're both pretty obviously named. Scan cache is something you will be scanning in the future, and copy is somewhere you're copying into. But they need memory. The copy cache is actually just a pointer to some places on the heap. So basically, it's just a spot on the heap for you. So every thread that's doing GC work will go, and similar to a TLH for allocation, it will go and just reserve chunks of memory so that it can copy into it without having to hit locks or anything. So it'll take up to 128K or 256K at a time to be able to do collections. So your copy cache is basically just a direct mapping down to some space in survivor space. So now that we have A, we're going to copy it. It will get copied over into this survivor space and updated in, it'll be present in your copy cache because it's the same memory. And I'm going to call them all prime here as I copy them over so it's easier to talk about them. So we've copied it over. At this point, we've just copied the memory in there. The way that we actually finish copying the object is we actually atomically swap in a forwarding pointer into the old location to point to the new location. So what that would look like is where A was before, we now leave a pointer over to where it is now. The forwarding pointer is actually just you can tell it's a forwarding pointer because all of our objects in our VM are aligned to a certain object alignment, which means we actually have the least two significant bits available because it's always zeros. So what we do in a lot of cases is when you're fetching stuff in the GC, we'll grab it and check to see if bits are set. So that's how we would do it in here. The lowest bit wasn't set, or second lowest bit, I guess. We've copied it over, but now we've installed this forwarding pointer here so that if anybody else sees it later, they don't copy the object again. They actually just update to the new pointer. The one thing to note is we actually copy first before we install the forwarding pointer. So because we do that, you can actually end up with multiple people copying at the same time. If there was multiple references, only one thread will win the atomic update, and that's the one now everybody sees. Depending on what phase if we are in the GC, we actually, and the size of the object, we'll just ignore that we lost and keep going. We won't give that memory back. So it can be wasted memory at that point, depending on the size of it. We have been implementing some other things to get it back, but for most of the time, the cost or in time isn't helping for the little bit that's wasted. So we'll step through now that we've actually swapped that in. The root set gets updated to point at A prime. D, we'll do the same thing. It moves over. And then we'll go to F. It goes. Now that we've finished the root set again, we actually have to have somewhere to publish our copy cache to so that someone could use it as a scan cache or we could use it as a scan cache. So again, we have a work list. At the end of root scanning or at any time one of your lists is full or empty, you'll push or pop to these other lists. But when you're finished, one of the phases like root scanning, everyone flushes things out, and then work becomes available for all the other threads. So what we would do is now that we want to go scan, because we actually have some pointers here and things pointing at really bad places, they're pointing at garbage, is we would actually take the top one off the list and make it as our scan cache. I've copied it into both just to highlight the fact that if there is actually still space in there, your copy cache and your scan cache can actually be one and the same. And in fact, we actually tend to favor that when possible, because then you're actually copying objects closer to their references. So for a lot of time, we actually will be aliasing our copy cache to a scan cache and actually scanning through it so that we can actually keep objects closer together. And on some real benchmarks and real-world examples from a few years ago, this can actually give you close to like a 5% throughput improvement in the way we have it implemented at your runtime. So we'll start stepping through the scan cache portion. A prime pointed at C, so we've copied C over. D had nothing. F is here. So at this point, we've gone through and updated everything to point over. So we've copied everything. Everything's now over at the end in this space. So again, we would continue this, getting caches back and forth and using them until we've completed the list as null, as it is now. So that would signify the end of the scavenge. So what happens at the end of the scavenge? So make all of those work states disappear. What we do is we actually convert, and I'll go back. Survivor space actually becomes allocate space, and allocate space becomes survivor space. We just sort of switch the logical term for them. And now from now on, for the next little bit, we'll allocate out of allocate space. You might look right now and go, well, you didn't actually buy yourself very much room. That's where our tilting and things comes in. We'll actually slide that down and take a lot of memory from the survivor space. So that's sort of how our scavenger works. And this is our current default collector. And for most workloads, it's probably actually the best out-of-the-box performance you're going to get for most things that people are running. Everything can kind of be tuned and do things, but if you're going to pick a starting point, this would probably be the starting point for a lot of people to go. Balanced. So Balanced is our newest collector. It's a region-based generational collector. It basically focuses on what we call partial garbage collections. So it's not a full garbage collection, and it's not as small as a scavenge. What it actually does is it will actually focus on collecting regions that it believes are very high return rate on the investment. So if you had a bunch of regions that only had one live object, picking all of them to perform your GC, there's not very much cost to copy all of the data. So that would probably be a very good candidate for being copied. It has a goal of no global collections. It's NUMA aware for allocation and for GC. So I'm not sure of any of the other VMs that are doing that right now for both. But for on large systems, we are actually completely NUMA aware. It has a significant reduction in your max stop the world GC time. Not your average. The fact that we actually include more than just your nursery space, actually your average pause time is actually slightly longer all the time. It's balancing them out and keeping your average very consistent, and your max is hopefully the same as your average. More barrier work. It actually has a lot of native memory growth compared to the other collectors, though. It has 2 mark maps. It has a work packets remembrance set, and then it has this, it has a remembrance set card table, so that's how it tracks inter-region references, and then it still has the copy scan caches that we talked about in GenCon. There is a full parallel global GC to fall back to if we need it, but the goal is not to do it, and I rarely see it in any customer workloads. So this heap is divided into fixed number of regions. The number of regions is based on your heap size. So the bigger your heap, the bigger your region size. We try and have between 1,000 and 2,000 regions, just so that we can have lots of work sharing capabilities and potential. And the big thing is the region size is always a power of 2. Some of that will become more obvious in a few minutes, but it really helps us with a bunch of things. And again, because we're NUMA aware, we try to evenly distribute the regions across NUMA nodes. It's not always possible. Not every NUMA machine with NUMA is configured so that it has the equal amount of memory on the nodes, but we do our best to try and configure it that way. So unlike GenCon, where you had this one fixed space where you're allocating from all the time, in Balanced, we allocate from our Eden regions, and they can be any free region from anywhere in the heap. So after a GC or at the start, you just pick any N regions that are free, and they become your Eden regions where all of your allocation is going to happen from. Again, it tries to distribute these across NUMA nodes. And the interesting part here is that your application threads will try and allocate from areas in the heap where there are NUMA nodes associated with, which on some applications can really improve your throughput. No non-array object can be larger than region size. We do not support humongous objects. I think that's the word G1 uses. We don't support it. If you try and allocate an object that's larger than region size, you get an out of memory. Not a great answer, but that's the current answer. I'm not sure I've actually seen this be a problem anywhere. For a regular object, how many subclasses and fields do you really have that your object individually starts being more than 2, 4, 8, 16 megabytes in size? It's usually held out for arrays. We do support large arrays, and they're handled as arraylets. This is something we've added for a Metronome that I'll talk about later, a long time ago. But basically what this is arraylets are discontiguous representation of arrays. To you as the Java developer, you wouldn't notice any difference, but the VM has actually divided this array into an arraylet spine and a bunch of leaves. This is kind of what it looks like. So your arraylet spine would have its normal object header, and then it actually has pointers off to the leaves. The leaves in this case are all region size completely. So you have to really start to have big arrays for this to be a thing too, but that's how it works. The calculation to get to an actual array element is actually slightly more complicated. But I'm using things here with index and using mod and div. But because we always have things as power 2, we can actually do some shifting operations and things instead. Uh-oh. All right. So those are slower. The other big thing is JNI critical sections really get in our way. They have to see the data as one contiguous block. So right now, what that means is you copy that into a malloc buffer, give it to them, they finish it, we copy it back if they have commit on. Not great. But we have some solutions for that. So what does the balanced heap look like? I've shown it. So let's say I pick these 4 light regions as our Eden space. So you would see that allocations slowly are happening across all of them, and that's usually because it's being distributed across NUMA nodes or just the way we do lock sharing so that we don't have any contention. And once the regions are filled up, it's time for a PGC. So the PGC is very similar to a scavenge. It's just a short one. We have this GMP that I'll talk about late in a few seconds. So we'll have GMP starts, and then PGCs going, and a GMP end, and more PGCs. The GMP is our global mark phase. It actually doesn't attempt to reclaim any memory or do any real GC work. What it actually does is it performs just a marking phase to build a mark map. This mark map is actually used by the PGC to predict or guess which regions have a lot of dead objects in them. They're interleaved in between PGCs, so once we get a good idea of how long we have in between PGCs, we'll try and schedule it in the middle, and we try and pick enough work that it's the same length of time as the PGC. So you'd see just still consistent, constant times of GC. So if we went to here, the green ones were used regions, blue is free, or green was the newly allocated ones. I have the orange. Yeah, I guess orange ones as older objects. So to pick for the GC, what you need to do is you always pick the Eden regions, and then you'll go through and you'll pick some of the old regions based on the criteria. So then you would collect it by performing the copy forward, which is the same as the one in GenCon. There's no need to go into the details. It's installing the same forwarding pointers and doing all the same work. And then you would just go through and now pick your next new free regions for Eden and continue on. So what do we need a barrier for here? It's similar to GenCon. You need the barrier to actually track. For every region, you need to know which other regions point at it, because if it gets collected, you need to be able to go update pointers in there and use those other regions as your root set. Straightforward. This is what the barrier looks like. Find your region. If they're not the same, go add yourself to the RSCL. So Metronome, it's our incremental soft real-time collector. It's actually been in our Java VM for about 10 years now. It has ultra-low pause times of 3 milliseconds is the default. I see customers have run it down with specifying 1 millisecond, and it still works. It's dividing the mark and sweep phases up into incremental chunks. By default, it lets the application keep 70% utilization, so it'll never kick off a GC increment if you're blowing in that time window. And it really produces a significant reduction in max pause times. It also reduces throughput quite a bit. So the heap, again, is divided into regions. That's where our first region-based collector. But these ones are fixed at 64K in size. So a bigger heap means more regions. So really big heaps means a lot of overhead for region management. So up to 30 gigs is the sweet spot. Over that, things start getting a bit much. It does cell-based allocation. So regions are assigned to cell size on the first allocate. Only objects of that size go in there. Again, it has arraylets because it does regions. Arraylet leaves here are only 2K though instead of region size, so that we can have smaller work units to be able to pause and do our increments. But we do support contiguous regions here. So these ones will actually do contiguous regions for large objects. And if at any point we couldn't get them, we would try and do a full stop the world, which basically falls back to an op throughput type collector. It's basically the same. So we would try that to see if we can get memory back, but that's the only fallback we have. So allocation in this one is sort of, you see kind of memory all over the place going. As we're going through, because it's all the regions. Every time you get a new size class, you need to get a new region for it. So you'll slowly see memory getting used up all over the heap. GC, sorry, I skipped too far. GCs are triggered by default at 50% heap free. So as soon as we have 50%, we kick off and start doing all of the GC increments. We continue to allocate while the GC is going. Basically, by the time mark is done, your heap is basically full. And you hope that your sweep phase, as you go, slowly starts freeing up memory for you. At the end, you go back to your normal utilization of your application. But if you actually didn't get 50% back, we just kick off another GC right again. So those are in really tight situations. But in this scenario, I would recommend, if anyone's using Metronome, to probably use like 20 to 50% more heap just so that it can keep up. What it looks like, GC start, and then it's just increments. Those are not full GCs. They're just really small pauses doing an increment until we're done, and then we move on. It uses a snapshot at the beginning barrier to keep track of the objects. So what this barrier means is it basically says that from the time you start the GC, everything that was live will be live at the end as well, including everything you allocate during that GC. So this GC, this type of barrier and this GC leaves a lot of memory on the table for like a lot of floating garbage. The difference is from the other ones is this barrier actually has to be done before your store because it's actually doing something different. It's actually remembering the object you're writing over. So we were going to write into field 1. We need to actually remember the value that was in field 1 because we've said that everything that was alive at the beginning will be alive at the end. So if your GC is active, you have to remember the object you're storing over. And then you go and store into the field. Does the exact same marking and sweeping as op throughput, except for all of our yield points actually do something in this one. In op throughput, they do nothing. Here, they're checking time. And as you start to get close to your time, it will actually yield and go back to the application. So just sort of a quick guide here. This is, if people grab the slides later or are looking right now, it's kind of listing the GCs and how I feel with their domains where they're best fitting right now. It lists sort of how much extra memory they all use, and a kind of my opinion on throughput for how well they're doing. A bunch of links for OMR, J9, and Adopt OpenJDK. Love it if any of you guys are interested, and go take a look at the projects. Any questions, concerns, feedback in any way. If things aren't working, that's I'd still love to know. Any questions? I have time for one. All right.
Hi. Do you have any numbers what heap sizes are and what possible pauses, maximum pauses are per heap sizes, especially for large heaps?
I have a bunch, so it depends on the collector too, so that's kind of really what you want to know. In GenCon, if you're sub 100 gig, with a nursery like 10, 20 gigs, it's really based on your live set. Smaller heaps, scavengers are usually in the small tens of milliseconds, 10 to like 50 milliseconds. Metronome is always 3 milliseconds unless we go over for some reason. Really big heaps though, like when it starts to come down to compaction, so I've seen things compact like maybe a 20 gig heap, 30 gig heap, you're starting to talk about seconds of collection time at that point. But really your interest is probably in balanced and GenCon, so the scavenge and PGC times are probably for most things in the tens. But if you start to get in bigger workloads, we try and cap the balanced PGCs I believe somewhere around 150 millis. If we won't take any extra work if we believe we're going to go over 150 millis. We won't do any fragmentation work.
Okay, so thank you very much. We have no time, unfortunately. Thank you.